So welcome back to lesson 3 in the Build Your Own Particle Simulator in Python course run by Amazing Potential. It's really great to have you on board, and I'm looking forward to doing another episode here, and I hope you find it really useful. The thing that we're going to do in this episode is add a second particle, which builds on the first episode, which we called our Hello World of Particle Simulation. And that created a single particle. It used the Pygame framework to be able to display where that particle is. And then we introduced some basic dynamics, so showing that particle move and bouncing off the wall. But the moment that you can start adding other particles, things start to get more complicated. So by adding the second particle here, we'll see how the complexities arise and what happens with those interactions. In order to do that, for those already really familiar with Python, I know you probably want to just jump ahead and do all of this in NumPy, but I want to keep this simple for now. We will bring NumPy into the mix later on, but I just want to explicitly identify the two particles before we get into the slightly more complex area of introducing loads and loads of them. So to achieve that, what you can do is, if you're not familiar with the VS Code method of being able to rename variables, is if you just click near the variable, as you can see it's now highlighted. I've not had to highlight it, so I've just clicked near it. Press F2, and you can see it says now we can rename it. So we're going to call this x1, and we just hit enter, and it will change every instance of that variable within our code. So flipping useful. We can do the same thing with our velocity for that particle. We'll hit enter after hitting F2, and there you go. We've renamed all of those variables now, which gives us the opportunity to add a second particle in the mix. And it's, nothing to be particularly sort of surprised by. You can guess what we're going to do. But in fact, actually, just before we do that, let's do the same with radius as well, because we might want to change the radius of our two particles separate to one another. I haven't done that in my videos yet, just because that can add a few more complexities with some of the kind of calculations that I'm doing at the moment. But at some point, I do want to also have varying radii in my simulations. So let's just highlight it, copy it, and then paste it here to add our second particle. And I'm just going to rename this, and you can't do the F2 now because that will rename everything, which we don't want to do. We want to explicitly just rename these ones to have a 2 after them. That's now identifying our two different particle coordinates. So the first of these, I'll just put particle 1, and then we can copy that and we'll put particle 2 here. And then just to make things a bit clearer as well, we can put, I'll just put other simulation parameters, and we'll keep for now the color of the two particles the same. Obviously we can change that as well later on, and if you want to, feel free to copy and paste that and put it amongst the things up here. That's also fine. So we've got a starting position for our first particle, starting velocity as well, and then a radius. As you can see, our second particle has exactly the same values. We've not changed those yet, but we can't have them starting in exactly the same position, because that's going to create some unphysical behavior, because the particles can't actually exist inside one another. So what we can actually do is let's just move the positions a little bit. So I'm going to place one at 125. I'll place the other at 375, sort of evenly spaced either side of the middle. And then I'm going to make their velocities go in opposite directions to start with. So they'll be going away from each other. They should bounce off the walls and then come back. Right, so we've defined that. So for now, we're not going to make them bounce off each other. We'll just make them non-interacting. So in a sense, a non-physical thing is going to happen. They will go through each other, but I want you to be able to see them separately when they start. And then we will add collisions between them. But let's take this step by step. So the next thing we need to do to be able to actually include the second particle is basically what we did with the first, right? So let's just copy and paste this bit here. Actually, it doesn't draw a solid blue circle anymore, does it? We should change that. Solid white circle. and fill the background with black. How did I not notice that earlier? And the same here. And I'll put for particle 1, and then we can say for particle 2 here. The next thing we'll do is we just need to rename this variable to 2, and then it will draw particle 2's position. And then let's also change the radius for that as well. So you can see we're now basically drawing particle 2. And then what we should add, as well as what we did before, which is handling the collisions, so wall collisions. So we've got handling wall collisions for particle 1. Yep. Oh, whoops. I've got a new microphone stand, and I can't actually see where my hands are when I'm typing. And I'm not a great touch typer. I'm all right, but I make lots of mistakes, which is why you're seeing me make some mistakes at the moment. I've got to get a good angle. I've not quite got it yet, so bear with me. So we've got handling wall collisions for particle 2. Let's just adjust all of the values here where it says 1 to be equal to 2, so that we can make those changes. And then finally, let's add some comments here. So we're going to say particle dynamics let's just call it dynamics for particle 1. And then, no surprises, dynamics for particle 2. Right. So just to recap, you can see we're drawing both particles here. We've not done anything kind of particularly shocking there right now. We're handling wall collisions for both particles here. And we're handling the dynamics for both particles. So we're updating the position of those particles based on a time step taken for each frame. We should, if all goes to plan, I may have made a mistake, but I think it's always more fun to just run it, and then we'll be able to see it really clearly. Here we go. Oh, what's going on? Particle 2 is not moving. What silly mistake have I made? But we can see there are 2 particles on the screen, so let's close it. I would like to say that was intentional, but it was not successful. Huh. For the eagle-eyed among you, when I copied and pasted that, you would have seen that I hadn't made the update, so that would explain why. Debugging is not too painful a process until, well, I'll tell you a story actually. So the worst ever bug that I've had to track down was in the early days of me making use of MATLAB. So I'd used it for probably maybe a year or 2, something like that. And the default font in MATLAB, at least at the time anyway, and this was probably what, goodness me, I'm getting old, 13 years ago, something like that. The default font looked no different for L and for 1. And I was trying to do a simulation of magnetic fields. And basically, the 1 and the L looked exactly the same. And I'd accidentally managed to multiply something by 1 when I should have managed to multiply it by L. How I'd managed to do that, given that L is on the complete opposite side of the keyboard, I do not know. But I spent 3 days trying to debug that because it didn't give me an error. It just gave me really weird magnetic fields. They were just not symmetric when I was expecting them to be symmetric. So what on earth? Yeah, so debugging when you have to do that is not fun. But in this case, it wasn't quite so troubling to find. So I think we should be able to run this again, and we should see now particle dynamics for both of them. There we go. And you should see that they'll go through each other, which is fine. That's what we expect. Yep. And then they'll bounce on the opposite side walls. All is good. So we can close that for now. So the next question is, how do we make them interact with one another? And this is a really important part of making any particle simulation. So we're going to add elastic collisions. You can have inelastic collisions, but if you're not familiar with what the difference between an elastic and inelastic collision is, for an elastic collision, energy is conserved and momentum. So in all physical interactions, momentum is conserved. So that's basically the mass times the velocity of your particle. That will always be conserved. That's not lost from a closed system. But energy can get lost in a collision. And the way to think about that is if you imagine sort of two snooker balls hitting each other, they can make a noise. That noise, making that noise, takes energy. So energy is lost in that collision, which means bit by bit, if you were in a frictionless system where you had snooker balls on an ice snooker table, bit by bit, they would still lose energy from those collisions. Another source of energy loss is heat. You can get some compression, internal kind of compression of the inner components of your particle. That compression can lead to heat being generated, and therefore heat can get lost from the system as well, and that's energy loss. So we are going to do full energy conservation. So there's no energy loss in the collisions, and because it's physical as well, there's going to be momentum conservation too. Inelastic collisions would allow you to lose some energy. It could be losing as much energy as is possible in the collision without losing any momentum, or it could be just losing a little bit of energy from the system. So let's have a look. We've got to have an equation to be able to work out what the outgoing velocities of the particles are, depending on the incoming velocities. So let's have a little look at some equations on Wikipedia. Wikipedia is our friend. I love it. It's a great resource. So I'm just on the page here for elastic collision, and this is for a one-dimensional Newtonian collision. And you can see here that the total momentum, it says here, is before and after the collision is expressed by this. So we've got the mass of each of the particles, which we've not yet defined. We just treat it as having a mass of 1 right now. But I think we will want to add some mass soon so that you can see what the effect of having particles with different masses are. But you can see here, it's the mass times the incoming velocity here of the first particle plus the mass of the second particle times the incoming velocity of the second particle. So the initial velocity before the collision, that's your u parameters here. And then that's just saying is equal to the sum of the momenta coming out of the collision for each of the particles. So v is the velocity after the collision. Now, we're going to skip ahead a little bit here once we've just briefly talked about kinetic energy as well. Kinetic energy is expressed as half times the mass times the velocity squared of the particle. So you can see here, it's just the kinetic energy of each of the individual particles coming in is equal to the kinetic energy of each of the particles coming out. And you can see here there's some resulting equation here to work that out when you've got mass included. We'll come back to that. But for now, let's just jump down here and we can see that this handy little trivial solution is presented, which is if both the masses are the same, we have the trivial solution, which basically says that the outgoing velocity of particle 1 is equal to the incoming velocity of particle 2. So essentially, they trade their velocities. So in other words, if they come together from opposite ends and have a collision, they will just swap their velocities. Likewise, if they were both going in the same direction, but one is faster than the other, it will just impart its velocity to the other. And the one in front of it now will have the faster velocity than the one that hit it initially. So let's just take account of that. So all we need to do, if you remember the wall collisions, right, we can just put another condition into place. So I'm going to try and handle the particle collisions before the wall collisions. I don't have any particular preference as to what order it's in. That's fine for now. If we discover we have a problem, we can handle that later on, but I've not had any issues so far. So we will just call this handling particle to particle collisions. And I just want you to think for 10 seconds, what is it that we're actually checking for here? Before I do it, what is it that we want to check? Okay, so I'm not going to give you any longer, but if you want to pause the video now before I give you the answer, please do. So if we want to check whether the particles have collided or not, the condition is that we care about the outer kind of edge of the particles, whether those are touching, or whether the particles, because we're taking discrete time steps, right? In one time step, the particles might end up inside one another very slightly. If they're going really fast, they might end up quite well inside one another, which is where we need to be a little bit careful about our time steps. But for now, they might end up just a little bit inside one another. So the condition basically is, if the coordinates, which if you remember define the center of the particles, if the distance between the coordinate of one particle and the other is less than 2 times, or less than the sum of the radii of the particles. So if you imagine, to be able to get from the middle of one particle, which is our coordinate for that one, to the middle of the other, if they were perfectly touching, it would be going through a length equal to the radius of the first particle plus the length equal to the radius of the second particle, right, to get through. And we should be able to see that in action in a minute. So what we need to do is we're going to check if x, and we're going to do absolute. Is it going to, yeah, I forget if, yeah, that's helpful. I always end up using a lot of the NumPy functions by default, so I forget what's actually a standard Python function. So let's give this a quick go. So it's the absolute of x2 minus x1. It doesn't matter what order this is in. That's absolutely fine. And that will tell us the distance between the two, no matter what order the particles are in, right? And we don't mind whether it's a negative effective distance or a positive. We just care about how far away they are, not the orientation of the particles. So we're saying if, just get rid of some brackets that we don't need. Oh, in fact, we will. Sorry. Oh, no, we won't. No, we're good. If the distance between the two particles is less than radius 1 plus radius 2, yeah? So the distance between them is less than the sum of the two radii, then they have to be inside one another as particles, right? There's no other way that they wouldn't be. And if that happens, what we say is that they just trade velocities. And there's a really nice way you can do this in Python in one line, which is really neat. You just basically go v1, v2 equals v2, v1. And I feel like that just shows you what's going on. It's just saying, based on this ordering, that they swap from one another. And in fact, I should actually remind myself that it's not just v, it's vx. vx1, vx2 equals vx2, vx1. So that's just the ordering of these has swapped around, and they'll get assigned to the opposite. So now that we've done that, it should be as simple as these two lines that we've added here. Yes, okay, we've added a comment, but I'm not counting that as lines. And by putting those two in, that should have handled all of the collisions that we need to. So let's run it and see what happens. Hopefully it will go as planned. Will they bounce? It's anyone's guess. Yes. So hopefully you're as pleased with that as I am. It's really satisfying when you see them bounce for the first time. And actually, maybe we can make them travel a little bit quicker as well. So let's stop it. And we'll increase their velocities. Let's go 250. 250. We should hopefully see them bounce quite nicely. Bounce. Still satisfied? Yeah? It's quite nice. Let's not make it so even. So what we could do is let's make them both travel in the same direction, but I'll just make one of them slower than the other. Let's see what that looks like. Yeah? See how they trade their velocities? Swapping which one's the fastest. That's a bit more interesting than the last one. It's not so symmetric, right? Okay. So now that we've done that, we really should add a new property of the particle, which again is something that I have got in my simulations, but I haven't really made much use of so far, which is to have mass for the particles, like a different mass for each of the particles. Let's define that here. So we're going to say mass 1, let's make this equal to 1, and then we'll make mass 2 equal to, let's make it equal to 10. So we can see how, it's basically like, I don't know, hitting a tennis ball with a ping pong ball or something like that. You'll be able to see the difference that it makes. And I will slow it back down so we don't get too much of a shock in terms of what might happen as we transfer momentum. But let's jump back to Wikipedia to see what the actual equations are if we want to update it. So here is the first equation. And in fact, what we can do is I'm going to bring this over this side, and then we can make our modifications here. So I'll just move this across there. So you can see what we did if we had a particle-to-particle collision. We've just got to make a little bit of a change here now. And it should be possible, if I've done this right, to still express it in the way that we have, but it may not be quite as tidy to do it this way. So perhaps in the sake of being tidy, what we can do is that we're going to make a variable that defines what the collision or what the velocities of the particles are prior to the collision, because what we don't want to do is to update v1 and then for that updated v1 to go into the equation for v2, right? So what we'll do is we'll just make vx1 and vx2 equal to a temporary parameter that just stores our pre-collision velocity, which we'll call ux1 and ux2, and that can go into all of our equations, and then it makes it look a little bit more like what's in Wikipedia as well. Vx1, Vx2, we've got here. I'm just going to define our velocities after the collision, and we can just take the mass of each particle. In fact, rather than me calling it mass, let's call it m. We'll keep it more simple. And you know what? For the sake of argument, let's do the same with the radius, because we don't need really long words for that either, and it just keeps the equations a bit more simple as and when we need them. So we can say it's m1 minus m2, yeah, divided by m1 plus m2. There you go. And then we multiply all of that by u1. So I can just do that here. I will go ux1 in the front multiplied by all of that. And then we're going to add ux2 multiplied by, and then you can see there's a 2m2. Let's just put 2 in the front here because I like to put my numbers in front of my variables. Times m2. Then we can go divided by m1 plus m2. It doesn't matter that I've switched around the ordering of the parameters. If you know, for me it was BODMAS, brackets, order, division, multiplication, addition, subtraction, for the way in which computers handle the ordering of your parameters, or how, when you put anything into, some sort of mathematical expression, which operators you should deal with first. So that's handling this. We're all good. In fact, I'll put a few little spaces around to just make it a little bit neater looking. So let's just review. We've got ux1, which is our u1 here, times m1 minus m2 over m1 plus m2. Yep, that's good. Multiplied by 2 times m2, we've got the m2 here, and multiplied by u2, ux2, and then divide that by m1 plus m2. So we're good. That looks really promising. Now, you can see here the expression for v2 is just the opposite way round, as far as I can see, except in the case of the minus, we flipped the numbers round. So rather than us getting confused and accidentally copying and pasting it the wrong way, I will just rewrite it, or write this one down here. So we've got m1 divided by m1 plus m2. And then you can see we also want ux1 there. That's our first expression. Yeah. Then I'm going to add m2 minus m1 divided by m1 plus m2. How am I doing with my touch typing? It's getting maybe a little bit better. ux2 times this expression here. I think we've got it right now. Hopefully that will behave itself. I'll just tell you one quick thing before we actually run this and see if it does what we want it to do. I was considering for this video just looking through a derivation of how we take these two equations of momentum conservation and kinetic energy conservation and actually seeing how we get to these equations. And it just turned out, actually, what I thought was going to be a really trivial exercise turned into too many pages of me trying to get to the answer and knowing what the logical answer was and not managing it. And then I discovered that there's like a really cheeky substitution that I had forgotten, which for those of you who might be interested, I'll just scroll down really quickly and see if I can find it. Here it is. So this cheeky substitution here is what tripped me up. I didn't think at all of putting this in to be able to get it. I don't know whether that deserves a slapped wrist or not, but I did not think of putting that in. So I think rather than, anyway, boring everyone senseless by going through a derivation, let's just put it into practice and see what it actually means for our code. We'll just now head back. Here's our particle-to-particle collisions. Should we run it and see? Have a think about what your expectations are for how the particles will behave. I'm wondering, actually, before... Yeah, let's do this. I know I told you we didn't need to have separate colors, but now that we've given them different masses, I think let's give them different colors as well, because then you'll know which is the heavier particle. So I'm going to make one particle, let's make it red. So that's the first parameters R for red, RGB, green, blue. So we're going to just make this fully red, no green, no blue. Then we'll make the color for particle 2 be blue, fully blue, and no red or... Oh, sorry, that's not blue, that's green. Fully blue and no green or red components. And then we'll delete the color here. And then we'll just update this to be C1 and this to be C2. And then it'll just be so much clearer as to what's going on. Okay, so now we know that the the blue particle, get it right, come on, that the blue particle is the really heavy one. It's got a mass of 10 in our units. Don't worry about things like SI units for now. We'll just call them for now arbitrary units. In our unit system, in our universe, we're just giving them a value of 10. So we're saying it's relatively speaking 10 times more massive than particle 1. So that means particle 1 should have much less momentum than particle 2 when it starts. And we'll have some interesting interactions in terms of how, perhaps when you watch it, they impart momenta to each other. It should take quite a lot of collisions from particle 1, I would have thought, to change the momentum of particle 2, because its momentum is so much smaller. But let's actually see if that's what happens. Let's run it. Here's hoping. What have I done wrong? Haven't defined C2. Just called it C1. There we go. Another bug fixed. Let's run it again. F5. Ooh, what's going to happen? Ooh, can you see that? Can you see what's happening? Yeah? So the more massive particle, blue, even though its velocity might be similar to that of the red particle, its mass is so much larger that it gives red a real kick. And it takes quite a few hits from the red to impart the velocity onto blue. Oh, ah. And this is the fun thing, actually, about watching this. Once you have different mass particles, you can create kind of really interesting scenarios in terms of how they bounce off each other. There you go. The system's definitely not as simple as it was before. Let's watch one more collision. There it goes flying. So you can actually see now, you can completely control the mass of each particle. Maybe what we should do, just for the fun of it, is let's change the radius of the blue particle to indicate its mass is 10 times larger. Now, as this is a 2D space, let's treat it as area giving the mass, not the radius giving the mass, right? So what that actually means is for it to be 10 times larger, we want a radius that is the square root of 10 times bigger than that of particle 1, okay? Because then it means that because radius is squared in order to get your area, right? So it means that when you square it, you will get something that has 10 times the area at the end of it. So we'll just go, yeah, we need NumPy for that. And we're not going to import NumPy yet. We're going to leave that for a moment. So let's just quickly go onto Wikipedia, not Wikipedia, onto Google, and just go square root of 10. I should know my square root of 10, surely, right? It's about 3.16. So let's go, well, that would mean 31.6, right? As our radius. Here we go, and it should look bigger and it should look more realistic in terms of its increased mass. If we assumed that the two particles were made out of the same material, you would expect then the radius or the area to look like the following. Should we see if it behaves itself? Collision should work. Yeah, there it goes, look. Let's have a little bit of fun with this in a moment. I'll just let that bounce off the edge. There you go, flying off. Doing exactly what we think it should do. I think you have lots of opportunities to try and make one absolutely massive and the other not so massive. You could end up seeing bugs. That's the only thing to bear in mind. If you go too crazy, and if a collision ends up meaning that the speed of the tiny particle is ridiculously fast, you might end up with some very strange behavior, which we might have to deal with later on. That would involve correcting the collision and making sure that the particles can't get stuck inside one another. That's one of the ways in which I've been able to handle collisions reasonably nicely with my code, although there's actually ways of improving that even further than what I've got at the moment. Let's just, for some fun, see what we end up with. We're going to make the mass of this particle now. I'm going to regret this, aren't I? This is going to be ridiculous. 100 times larger, which means that the radius, square root of 100 is 10, so the radius should be 100. Or maybe, is that going to look ridiculous? Well, let's just do it for fun, why not? We'll run it. It may error in terms of the numerics of it. We may end up having some problems, like I said already, but no harm in trying. Here we go. Oh dear. Oh. That's actually gone better than I could have possibly imagined. Take a look. Here we go. How satisfying is that? This just reminds me of one of the is it 3 blue 1 brown? I often get it the wrong way around. Video where he talks about how many collisions there are between masses that are like orders of magnitude different from one another, and somehow if you do powers of 10, it ends up printing out like digits of pi or something like that. That was pretty crazy, but yeah, it looks like one of those videos. One more time. Oh, look at that. I'm super happy with that. I hope you are too. And I think that's a great place for us to end our particular lesson today. Have a great rest of your day, and I'll see you at the next one. Thanks. Bye.